Yes.
Okay. Yes. Okay. So, hello everyone. Thanks for being here. Sorry for being late. Um, so I'm Maxime Elkael. I'm doing my PhD here at Telecom Paris with Andrea, who's here, Buddy and Ins, who are, I think Ins online, and Buddy is, I'm not sure. And so I work on reinforcement learning and optimization for energy efficiency, resource efficiency. So this is kind of my thesis rehearsal. This is a work I've been doing with at Telecom Paris and with Davidson Consulting. So thank you for being here. So I will start with stating the goals of my thesis. So there's a few. The first one is to try to enable applications on mobile networks with tight quality of service constraints. So think delay, jitter, these kind of constraints. Also, the other goal is to try to reduce the energy consumption of the network and the computational resource consumption of the network. So networks have a very significant impact in terms of energy consumption. So that's one of the main goals. And also the goal of this thesis is to try to address these problems of resource allocation and of energy efficiency in different domains of the network. So the core network, the edge network, and the radio access network. So I will explain, we will use mainly the concept of network slicing to try to do this. So I will explain a bit more what it is first, how it works. I will also explain then the architecture of the network. And then I will go into more of the contributions of my thesis. So first I will talk about the core network placement. So placement in the core, then the edge, and this will be more focused on energy efficiency. And finally, and then I will talk about IAB, so integrated access and backhaul, which is closer to the radio access network, and also from an energy optimization point of view. And then I will conclude. So first, what's network slicing? So the idea of network slicing is that now networks are evolving and we have access to network virtualization. So broadly, what this means is you have an example of the idea here. We have an operator who has a physical infrastructure. And so this infrastructure is heterogeneous. You have routers, you have firewalls, you have radio access points, all sorts of equipments. And most of them can be virtualized. So we can instantiate software on them and run different services. We can do a lot of things basically on this. And the idea of network slicing is to instantiate virtualized networks for tenants. So think, for example, Netflix, Renault, the people that have clients to serve and specific use cases. So the idea is that by enabling customized networks, we can enable customized use case. For example, if you provide an autonomous vehicle service, you want very low delay, very high reliability. While if you have a sensor network service, then you want your devices to consume less energy. So maybe you will remove some parts of the whole stack of the network. And if you do virtual reality, you want a higher throughput, and you care about delay, but it's not as critical. So that's the idea behind network slicing. Customized quality of service, isolation and security are also very important aspects that I don't treat in my thesis. So in that thematic, there are different aspects you can think of. The first, I would say, is the slice design problem. So the idea of that one would be to go from the business use case to a network specification. And then you have the placement and the resource allocation, where you have the network specified and you want to place it in the best possible way, given some objective, in my case, energy or resource consumption. And the third thing you could think of is slice management. So after the placement, how do you handle the life cycle? So maybe you have to scale up or down your resources to handle more users, these kind of problems. So I will now talk about the architecture of the network. So broadly, the network we consider has several components. So this would be the architecture of a classic cellular network where you have base stations that directly connect to the UEs. And then these base stations talk to a core network through the transport network. So you can think of routers here. And then the core network can provide services, provide an interface to the internet where you can have services available. The main difference with from what has been considered in the past and what we consider in this thesis is that we add those edge servers. So we have servers close to the users that can enable us to sell them some services at the edge, so with lower delay. So if you have to define the network in several parts, the core network would be before 5G, the core network was a big monolithic service. Now it's a lot of small services, and each of them can be adapted and scaled depending on your use case. So that's one part where we need placement and we need resource allocation to do that efficiently. The second part, the edge, would be more to place resources close to the users. So for example, if you have an autonomous vehicle service and you want to serve, say, in less than 5 milliseconds, and you need an AI or something at the to serve the client, then you typically want to place it on the edge because you want that very low delay, which you won't get if you have to go through the core and then on the internet and back. And the transport network is also programmable. We could talk a bit more about SDN and software-defined networks. But basically, there are technologies that enable you to reserve bandwidth and paths on your network. So I will now talk about the core network placement. So the first part of my thesis. So in that problem, we consider that we own a physical network. So, and we have tenants that come over time and they want to place slice requests. We have some limited resources. So here we consider CPU and bandwidth. And the objective is to maximize the number of slice requests that we manage to place. So broadly, this would be a slice. So it has some CPU here on the nodes and some bandwidth on the edges. And this would be our physical network. So those numbers are demands. And the numbers here and here, they are capacities. So you have to place this slice on this physical network. So a possible placement would be this one, for example. And you see that each node is placed on one node, one physical node, and each virtual path link, is placed on a physical path. For example, this one is placed on two edges. And we place slice by slice because there's been some work showing that it's NP-hard even to place just one slice. So what I mean by slice is that over time, we have arrivals. So we place, like I showed before, for example, slice 1 arrives, and then slice 2 arrives. We place it in a certain way. And then when slice 2 leaves, well, it frees the resources. The objective in this problem for us would be to maximize our reward, which is defined as the operator's benefit. And so it's the revenue of the operator divided by the cost of operating the sites. And we consider that the revenue is equal to the sum of the bandwidth and the CPU demanded by the user. So the more resources you ask for, the more you have to pay. And the cost is the cost to effectively, it is the number of resources you have to use to run the slice. And what's nice with this function is that it is always between 0 and 1. So it's a nice way to evaluate the quality of the placement, because basically if you place a slice such that all the paths are of length 1, then you obtain a reward of 1. And 0 would be when you fail to place, when you don't find a physical placement.
So very quickly, so for the study, what's the difference between CX and RX?
The difference is this is the demanded resources, and this is the resources you use in practice. So if you look at this here, for example, you will have 10 plus 8 plus 6 plus 7 plus 4 plus 11. And the used resources would be 10 plus 8 plus 6 plus 7 plus 11. But you see this link is placed on a path of length 2. So you would have 2 times 4.
So you aggregate CPU units and value units at the same time.
Yeah. Here you could just add the factor to say, okay, maybe CPU is worth more and bandwidth less. In practice, mathematically, it's just nice to have it between 0 and 1. But yeah, you could definitely do that. It doesn't change the approach. And we didn't really have data on what costs more for an operator to operate. So we considered it was equal. Yeah. So we have several constraints. So CPU constraints, you have to make sure you place a node, a virtual node on a physical node that has enough CPU. We also have bandwidth constraints, which should be there, which is basically the same as CPU. You have to have enough CPU and bandwidth resources. We consider that each virtual link should be placed on a unique path, not on a flow. You cannot split the flows. And we have and if 2 virtual nodes are in the same slice, we consider they cannot be placed on the same physical node. So this one can be relaxed very easily in our approach and in most approaches in the literature. It's nice to have for redundancy, but it's not mandatory. You can adapt this one. So to solve this problem, this is a problem that has been quite well studied. There were some classical optimization approaches. So think in our programming, some heuristics, either based on the integer linear programming approaches that existed, or like stuff like random walks. Like there's a lot of heuristics, and you also have meta heuristics. So those are also were also very trendy, and the ones that when I started my thesis were starting to gain traction, reinforcement learning, which are my interest for this part. So there's mainly 2 types of approaches. Monte Carlo research, which is the type of approaches I chose, and deep reinforcement learning, which is based on neural networks. I will dig a bit more on the difference between the 2. So deep reinforcement learning could be said to be offline, in the sense that you train a neural network for a very long time. So typically in the paper I was just citing, it's 72 hours on 24 simulators. And then you obtain a train agent, and your agent is now very fast to solve the problem. And it's supposed to be general, although it has caveats, because, for example, in this paper and at the time when I did this work, at least, all the other approaches, you would train for a single physical network. So if your network changed, you would have to change your agent to retrain for a very long time, etc. So instead, we choose to go for online reinforcement learning. So the idea is you have to retrain every time you have a placement, but the training is very fast. And so this has the nice properties that you don't need to retrain for several days when your network changes, or maybe when your slices change, because this, like, the fact that the slices could change, I think, has not been very well studied. And so our main contribution here is to propose an online reinforcement learning algorithm that improves the number of slices accepted compared to the state of the art. So in our solution, we place the nodes one by one, and then we place all the links at once. So link placement itself is NP hard, so we use just a shortest path heuristic. So since we do reinforcement learning, we have to define our system as a Markov decision process. So this is what it looks like. So we have a state that's comprised of two lists. So here is the list of the nodes to place, and here is the partial placement described in this vector. So basically, at each step, we take the first node to place of the list, so here 1, and we decide we take an action, which is to choose where to place it. So for example, here 1 is placed on 3, and so we put a 1 on the third component on the vector here. And then on the second step, same, we take 2, and we place it on 5, so it's here. And until we don't have any node here. And so when we have placed all the virtual nodes, we can place the virtual links and then calculate the reward, because the reward depends on the bandwidth that's consumed. So if you think about it for a bit, you will see that there's no stochastic element in this model. So the MDP looks like a tree, and the MDP looks like a tree. Basically, when you take an action, you are sure of the state where you will end up, and you can reach a state only from one sequence of actions, because our virtual nodes are ordered. So for example, if I place 1 on node 1, I'm sure I end up in this state. And then if I place 2 on node 4, I'm sure I end up in this state, etc., etc. So to solve the problem, we chose to use an approach that's adapted, that has been devised for this kind of problems that are deterministic and typically have a tree shape. And it's called nested rollout policy adaptation. It was devised at first for single player games, so puzzles, and got some world records on some of them. So it's an algorithm where we have two parameters, a level of search, L, and a number of iterations per level. And it's an algorithm where we maintain a weight for each state action couple. And so it's quite simple. I will go through an execution then, but there's basically 2 states. Either we are at level 0, where we do a simulation. So a simulation means take the weights that we have and use them to randomly choose a placement. Or we are at a level different than 0, and then we will make n level L minus 1 calls. So for example, we start with an initial policy. So all the weights of all the states are set to 0, and we make a level 2 call. So the level 2 call will make a level 1 call, which will make a level 0 call. We are at level 0, so we do a simulation. So at first, the simulation is completely random because all the weights are 0, and we get some reward for this first sequence of actions, say here 0.4. And then we will do the adaptation procedure, which is to increase the weights of the best sequence found so far. So at first, the only sequence we found is the one where we had a reward of 0.4. And then we do another simulation, and we will find another reward. And then we will take the best of the 2 sequences we found, and we will adapt, so increase the weights of the best sequence we found. And then we will do that again and again. And over time, our policy will converge towards the weights will increase for the best sequence. And so the idea will be that we want to explore at close to the best sequence. We found a good sequence. Maybe there's other good sequences of actions that resemble this one. So if I take the tree back, basically maybe I will do a first random simulation, and I will obtain this sequence, and so I will increase a bit the weights of this sequence. The reward was 0, it's not very good, but well. Then I will do another simulation, and now I find this, so randomly, and maybe I will find this one, which has a reward of 0.94. So it's better than 0, so I will increase the weights of this sequence. And so maybe I will do another run, and I will find this sequence again. So I will, well, another one, but I won't find something better. So I will increase the weights of this one again because it's the best I've seen so far. And again, my policy will hopefully converge towards this one. So this is nice. The issue is, for example, here we have a reward of 1, and we take no information from the fact that this sequence was good to try to find this one. Basically, we would have to redo the whole search to maybe find this solution. So that's the basic observation that motivates neighborhood enhanced policy adaptation, NEPA. So the idea is to take the same algorithm and to use an observation, which was that you can improve quite easily the solutions by running a neighborhood search on the solutions. The problem is if you do that on all the simulations you have, well, this will take a lot of time. And if you do that only for the final sequence, well, you will improve it, but you're not sure you improve it the best you can. So there's a trade-off to find. And the ideal would be to improve only the good solutions that we found, so we can also learn from them and include that knowledge in the algorithm. And it's quite easy to do because, well, in the structure of the recursive structure, we know that, for example, at the end of level 1, what's returned here is the best sequence found already. So if we refine here at level 2, we know that we will refine a sequence that's already good. And so that's basically what we do with the NEPA. And the nice property with that is that you do very few refines and you learn from them. I won't detail how the neighborhood search is done, but basically it's based on the idea of trying to move some nodes around and to improve the solution that way. And so basically in the paper, we called it a monkey business approach because the idea is to jump from a tree branch to the other one. So I've done a lot of numerical experiments on this approach. So I compared it to Monte Carlo research, to a meta-heuristic, and to GraphVine, which is neural network based. And the comparison was done on real topologies from Topology Zoo. It's a data set available online, and also on random graphs. So this plot shows the acceptance ratio, which is the main metric we look at. And basically what we show is that NEPA improves upon all the other approaches on most cases. On some, everyone is close to 100% of acceptance. I mean, not everyone, but NRPA and the neural network-based approach. But basically, yeah, generally on those ones, we are better than the state of the art. This is also the case on synthetic topologies, where this is also the acceptance ratio. Yeah. So now I will talk about the edge placement problem. So the second part of my thesis. So in that problem, we also are the network operator. And we have service providers that come to us and they want to place slices, so edge slices. So now the slices are made of a set of point-to-point flows. And so each of those slices have different quality of service and resource requirements. We didn't look at the delay before, but in this part, we are very interested in the delay because we are looking at the edge network, and that's basically where most of the delay constraints would be. And we are given all the slices at once, and we want to place them all. So the goal of this approach, this work, was to try to find an optimal solution, an exact solution, and to model the problem. So maybe I can comment on this network. So for example, here we have the orange slice A, that is comprised of 2 flows. One that comes from here, from this base station, and then goes to this edge server. And the other one that comes from here goes to this edge server. And we have the path here from the base station to the server. So intuitively, the requests that the tenants will ask us is things like, I will have 20, 30 users in this zone, and they will require this kind of services. So I know the number of operations, I know the maximum delay, and I know how often I'm okay with violating it. So for example, 99% of my requests have to be solved in less than 5 milliseconds. And so we have this as a constraint, and we want to minimize the energy consumption of the network. And we also want to place all the slices here. So when I talk about delay, I'm talking about this. So what I call the total delay is the delay on the path. So to go to the server and to come back, plus the processing time on the node. So basically, the more CPU I give a software service, the faster it is. But I don't consider the queuing delay at the router here because we consider that we reserve bandwidth similar to before. And so if you reserve bandwidth as a tenant, it's on you to make sure that the throughput is low enough that the delay, the routing delay, the queuing delay at the routers is negligible. What I call a placement in this problem is two things. First is to reserve CPU. So reserving CPU means you have to choose where to place the software component, and you have to choose how many resources you give to that software component that you just placed. The second part of the placement is to reserve bandwidth. So from the source, so the base station, to the place where you decided to place the software. And so we have to respect the required delay distribution, so our quality of service constraint, and to minimize the energy consumption. So we formulate this as an optimization problem. I will go through each equation. So in this problem, we have FKP, which are binary variables, and they are equal to 1 if a path is used. So for example, here in this example, if this path is used, well, the variable that corresponds to it will be equal to 1. And for example, the variable equal to this one would be equal to 0. And then we have binary variables, A, that tell you if a node is turned on or off. So, for example, R1 is on here, and basically all the nodes are on here because all the nodes have a path passing through them. L would be a continuous variable. It just serves us to calculate it's the utilization ratio of the CPU. So if I reserve 20% of the resources on a node, LVI of that node would be equal to 0.2. And mu is a continuous variable. It tells you which service rate has been chosen for a given service of the flow K, given that this service uses path P. And it is directly linked to the number of CPU resources that you allocate to that container. So yeah, I will now go through the objective function. So it has two parts. The static part of the energy, which is the cost you have to pay for turning on the node, and the dynamic part, which you pay, not pay, sorry. The static part is the amount of energy that's consumed when you turn on a node. And the dynamic part is the amount of energy consumed that depends on the load on the node. So that's why there's the ratio here. Then the constraints. So we have a bandwidth constraint first. Basically you cannot allocate more bandwidth on an edge than you have. Similar to before, each flow has to be placed on one path exactly. Then the physical node should, same as the bandwidth constraint, will have CPU constraints. You cannot allocate more CPU than you have. This constraint, what it does is it just makes sure that the variable corresponding to activating a node is equal to 1 if that node is used. This formula is just for calculating the CPU ratio. I won't go through it that much. And the most interesting constraint here is that one. So that one tells you that the service rate of your service, so equating to the amount of CPU, of each software component should be set so that the total delay that I just defined is lower than the delay demanded by the slice tenant with a certain probability. So we call it the service level. That's also defined by the tenant. And what's tricky is that this formula, it depends on how you model the requests and the arrivals, but it's nonlinear in general, and it's non-convex. Yeah. So in our case, we consider that the requests are of exponential size in terms of number of operations to perform, and they arrive following a general independent law. So you can, since this part of the delay is basically static, it depends only on the distance, only on the distance. The rest of the delay, the processing part, can be seen as a GM1 queue, basically, which is nice because there's a formula to calculate the delay distribution of the GM1 queue. Although it's not that straightforward to use because it's not linear. So, and what's also nice is that the processing delay is a function that decreases as you allocate CPU. The more CPU I give you, the faster your service is. And so that's a property we use. I won't detail how, but that's a property we use to calculate the minimum amount of CPU that we need to use in advance. Basically, what we say is that since if I give you more CPU, it will only reduce the delay. I just need to find the minimum amount of CPU such that your delay constraint is satisfied. Because if I give you more, you will just have a lower delay than what you wanted. We don't care that much. So in short, we use those properties to remove that constraint and that variable, and instead to just have this CPU KP here as a constant that we pre-calculate. So for each path, we can calculate in advance the amount of CPU that we will need if we use that path. So now we have an integer in our program, which is nice. We could give it to a solver. The problem is there's exponentially many paths, so we cannot just do that. So the solution we propose is to use column generation. So the idea of column generation is to solve only with a subset of variables here. And so maybe one path per flow. And we will get a solution, but it's not optimal for the whole problem. But we can try to identify promising paths that are excluded right now, but we can include in our problem. We add those paths to the problem, so those variables. We resolve, and we do that on and on until we cannot improve anymore, which means we solve the whole problem without looking at all the variables. So there's a lot going on behind the scene to do that. Mainly the big thing to do is to show how to choose those variables. And in my thesis, I show that solving that problem of finding the best variable is equivalent to solving a bi-objective shortest path problem with also forbidden paths, so not considering all the paths of the graph, which is not a polynomial problem. But we propose a method that's quite fast in practice to solve it. So this enables us to solve the full problem. So yeah, here are the numerical results. I compared this approach with a resource minimization problem, basically the same problem with a resource minimization objective instead of energy, and also with a VNE approach from the previous chapter that was slightly adapted. It's a meta heuristic. And so what we can see is that we save quite a lot of energy in the base, even at best here, we divide by 2 the energy consumed compared to a resource minimization approach. And we don't consume that much more resources. In this case, for example, almost none, but I mean, we don't gain that much. But even in the case where we gain the most, we don't consume that much more resources. However, the issue is the computational time. This approach is much slower to to run. Clearly, energy minimization is a harder objective than resource minimization. I can talk a bit more about that. I did some theoretical works to investigate why. Yeah, but that's the gist is we save energy, but it's a hard problem to solve. And intuitively, what we do, if you compare, this would be the resource optimal placement that I showed at the beginning. If you look at this flow 1 of size B, you would see that, so the blue one, you would see that we only use 2 hops to place this path. And this is fine, but we use less resources than if we do what is done in an energy optimal placement, which uses 3 hops, so more bandwidth is used. But in exchange for that, we don't use router 2 here, and so we can shut it down and save some energy. So that's basically what our algorithm is trying to do. I will now go through the third contribution very quickly. So the contribution is concerned with integrated access and backhaul. So the idea of IAB, or integrated access and backhaul, is that you have base stations and you want to cover typically a dense scenario, so maybe a festival, this kind of stuff. And however, if you want to lay a lot of base stations, you have to lay fibers. It's very expensive. Sometimes you cannot do it. If you have, say, a festival for a week, there's no reason to dig holes to put fibers everywhere. So maybe you want some mobile base stations, this kind of stuff. So the idea is in our case, we have one base station that has a fiber that is connected to the core network, and the rest of the base stations, they don't have it, and they have to do the backhaul, so to route the traffic from the UEs to the base station with a fiber, so which we call the donor, in order for them to have access to the core network. And so the question, there's a lot of things going on here because you can change the topology dynamically, you can reserve bandwidth in advance, you can shut down nodes and turn them on when you just need them, which is what I'm mostly interested in, because it means you can save energy depending on the current demand. So in this model, we have 3 types of nodes. The donor, which I showed, that has a connection to the core network. We have the other IAB nodes, which don't. And the UEs, so the users of our network. And we are given a measurement graph, which tells us the bandwidth on each link, depending on the channel conditions. And our goal is to find the tree topology such that all our UEs have enough bandwidth to perform their services. Like every UE will say, for example, I need 100 megabits per second. And so we have to give them that bandwidth. So this is what the measurement graph would look like. So you have here 3 donors, 3 IAB nodes, and the donor in red, and the UEs are in black. So we have measures of the channel conditions, which give us the amount of bandwidth. And then that's a possible tree topology that we find, where you see all the users are served, and the IAB node on top is turned off. So for this problem, we also formulated it as an optimization problem. I will go through it quickly. So we have also variables A, Vi that tell us whether a node is turned on or off. We have here variables that are not path variables, they are arc variables. So for example, if you take the measurement graph here, FVI-VJ of this arc will tell you whether this arc is used or not. And FKVI-VJ will tell you if the flow of one of the user K is using this arc. So for example, if this user is using this arc or this one. And those are all binary. Then we have those constraints. I won't go into too many details for those. So they are flow conservation constraints. They tell you basically what they tell you is that what enters a node, it has to be equal to what goes out of a node, excepting for the node that sends the traffic and for the donor which receives it. Then we have this constraint, same as before. It's an activation constraint to make sure that the node is counted as turned on if it is used. This constraint is also an activation constraint. It tells you if any flow uses an arc, then the arc has to be turned on. And finally, this tells you that you have to have exactly one outer arc turned on per node. This makes sure we have a tree. So you see here, for example, this one has exactly one arc turned on, and this one too, and all the UIs too. And finally, the first constraint, the challenging one, is the bandwidth constraint. So what it tells you is that if you have several inner arcs turned on for a node, then the bandwidth available is divided because there's only one radio interface. So for example, if you take this node here, there's 3 arcs pointing at it, which means that the capacity those nodes have access to is divided by 3. So this means basically we assume that the scheduling is done in a round-robin fashion. So this is the challenging constraint because it's nonlinear and non-convex. So the solution, very intuitively, that I propose to deal with it is to, instead of minimizing the number of nodes of the tree, minimize the number of arcs, which is equivalent because a tree exactly has n-1 arcs if it has n nodes. And in doing that, then there's ways to formulate this formula in a discrete way. And I won't detail that too much. But basically, there's a way to linearize, which is one of the main contributions from a theoretical standpoint of the paper. So in terms of evaluation, we used realistic scenarios. So we used LiDAR data of Milan, LiDAR scans of the city. And then from those LiDAR data, we can use the geometry to use an existing approach to place the base stations. So this is an approach that uses the coverage algorithm. So trying to cover as much of the city as possible. The UIs are placed randomly. And we use a ray tracing channel model to compute the bandwidth of each link. So after all this is done, we have the measurement graph and we could run the approach. And also to place the UIs, what we did is we took real density traces of UIs, and this enabled us to choose the density according to real life data. So this is what an instance would look like. For example, we have the donor placed here and the other IAB nodes in blue here. You see that most of the UIs are inside the buildings. That's because that's what 3GPP specifies. So 80% of the UIs are inside and 20% outside. And then once we have this, we can we can run the channel model, and that gives us the measurement graph, and then we can run the approach. So that's what we did, and we compared the approach to several approaches. So the first one is no relay, so you just turn on the donor. The second one is one where you turn on all the nodes and you try to route using shortest path. The third one is widest tree. So there's a mistake here in the slides. It shouldn't be all the nodes turned on. It's you compute a tree using a widest path approach, and you use that to route. Yeah. So it doesn't turn on all the nodes. And basically what we show, so the main result is that we activate, so this result is an average Monte. So we activate less base stations than the widest tree approach. And of course, we cannot compare in terms of number of base stations to no relay because it's only one, and to the shortest path approach because it always has all the nodes turned on. but we on average use less base stations than wider tree, and we follow quite closely the UE curve, which means that when there's a lot of UEs, we turn on more base stations, and when there's less, well, we manage to shut down our nodes. This is a second very important plot, because it shows that, so we set the bandwidth demand of all UEs to 80, and this is the minimum amount of bandwidth that the UEs demand. And what we do see is that basically our approach is the only one that manages to satisfy all the UEs. The other ones just can't cope with it. And this is the runtime. That's the main issue with our approach. We limited the runtime to 10 minutes. And you see that we often hit the limit. So yeah, that's the issue with this approach. It's slower. Oh wait, and I want also to give an intuitive view of it. This is what placement looks like over the week. So basically, this is the Monday at night. You have less UEs, and as you add UEs, well, as the day goes, there's more UEs because there's activity in the zone. And so you see they arrive, and we turn on the base stations, and then it will be night, there's less UEs, and so you turn off the base stations. So now I will conclude. So in conclusion, we did several things. First, we optimized the resource consumption of and placement. So for the whole network. So first in the core, we minimized the resources, and we combined reinforcement learning and neighborhood search. For the edge, we did energy optimization, and the big challenge was the quality of service constraints, and the big contribution is that we solved it with an exact method. For IAB, we also did energy optimization with an exact method, and yeah. Also, one big takeaway I had with my thesis is that energy optimization is inherently harder than resource minimization. Resource minimization has been studied a lot in the literature for a very long time, and less so for energy optimization. And so one theoretical work I did to try to understand why is to try to take the multi-commodity splittable flow, which is basically only the path part of these problems, but without even having to choose a single path, you can route on a flow. And so this is a very famous problem, and it's polynomial when you take when you look at resource consumption. So it's kind of at the root of those types of problems, be all three of them. And what I've done is I tried to see how hard it was to solve with energy optimization instead of resource minimization. And I've shown that it's NP hard, even in the case where you have a single flow, two flows, sorry, while it is polynomial with any number of flows in case of resource minimization. So that's one first theoretical understanding. And also, because of this complexity, the question is whether we can adapt. Now we have exact methods that enable us to benchmark, but can we adapt those the methods I proposed for the core to energy optimization problems? Besides this, I have more long-term perspectives that I want to explore from this thesis. The one question is whether we can solve those problems by leveraging the structure of the network. Like if you look at topology zoo, for example, most of the networks are planar. They have low tree width. So this is the kind of properties that are known to help with the resolution of a lot of NP-hard problems. So maybe that's a good thing to explore to try to solve those problems, and also to find approximation algorithms maybe on those type of cases. The second perspective is end-to-end optimization. So can we try to not do those different solutions in a vacuum and try to link them together be it in terms of implementation, but also in theory, probably the model would change. I've tried to do like some very early works on options with reinforcement learning at some point of my thesis, which the idea of those type of approaches is to factorize the states of the system to try to help to reduce the complexity. So maybe that's one way to do it. And also one question that I didn't look at too much, I also did early works on it, is run slicing. So how do you optimize the resources when you look only at one base station and you have UIs around? So there's a lot to do there from the scheduling standpoint, from the resource allocation standpoint that I want to explore more. Yeah, that's it. Thank you. Then, okay.
Une question au milieu qui t'arrive un peu coupée.
I didn't understand that we are in a repetition.
Okay, no problem. Any question? Yes.
Can you go to slide 23?
20?
23. I expect between 20 and 30 users. From where you take this information and where are these users? They are 20, 30 users in a coverage area, so in a base station or in a specific area.
So it's close to one base station. Basically, the client will say, okay, near this base station, I expect 20, 30 clients. So you would have them maybe here on this.
And do you have any reference for this?
For what?
For this information?
No. Yes.
Okay. Thanks for the presentation. You mentioned, I think it's in the first problem, that you apply online learning and it's fast. So what do you mean by fast? And what's the amount of data that you have used? Because I work in cyber, which is different, but I'm not sure if online learning is useful to me because I manage huge amount of data, but you say it's fast. So.
Yeah, so in my case, what I call online is not online learning in the sense of Bayesian learning, and it's really like it's really talking more about like Monte Carlo research approaches. So you have the runtimes here, and for example, I run those for 0.5 seconds. So for each slice, I run the approaches for half a second. So all the results you see, all the approaches have the same time. So half a second. And you have another question.
So, okay, online you mean in real time or something?
Yeah. Not in the sense that you adapt to the network, but it's we don't have a notion of regret or these kind of things.
Oh.
Yes.
Yeah, maybe one question on the definition for slice.
Mm-hmm.
Your study or your proposal is based on how to less consume CPU and memory. What do you think about radio frequency actually to define stuff?
Yeah. So it's not presented here and not even in the thesis, but I spent the last 6 months on this part. I know how I played with at least one implementation in OAI. It's not yet in public OAI, but a version with slicing. And what was done is you have your base station, and for each, so a slice is basically just an ID for the PDU sessions, and you can have a group of users that belong to the same slice because they connect using the same ID, basically. And at the base station level, how it was done in this specific implementation is that for each slice, so for each group of users, you had a different buffer of data to send. So if you look at the downlink, and so you have this buffer of data to send for each, and you allocate PRBs for each of those buffers. So maybe you can give 20% of the PRBs to one, 30% to one, and 50 to the rest. And then you can set a minimum, maximum amount depending on the demand. What else to say about it? I mean, it was, and it still is an ongoing work to measure. I worked on measuring the delay on those kind of systems. And also there's a whole question on scheduling, because you talk about PRBs, maybe you give 20% to one, 30 to the other, and 50 to the third one. I mean, by one, I mean slice. But then the question is, for each of those portions of PRBs, you can also change the scheduler. So yeah, that's a perspective I'm interested in the radio optimization part. For example, what if you know that your slice has some deterministic traffic, which in some 3GPP specifications you have, for example, for vehicles. Then if you have deterministic traffic, maybe your scheduler should be adapted to that. So it can do things better, because you can specify a different scheduler for each slice.
Maybe my second quick question is just to understand better the energy optimization part. I didn't really understand why not just modeling the VNE by adding constraints covering this story of energy.
Yeah, that was a question we had at first. The issue with VNE is that first the CPU is fixed, so you will have to accept having dynamic.
For you, the energy is the CPU consumption, right?
No.
No?
In that problem, no. The CPU is the energy has two parts. So here the first part is whether the node is turned on or off. And so E is just a factor. It's like basically it would be maybe equal to 200 watts if you have a server and 20 watts if you have a router. It just tells you the idle consumption of your node. So if you just turn on your node, you have to consume some energy.
But when we run applications on this service, so the consumption will be higher, right?
Yes, right.
How do you have tools to monitor this? You get this energy consumption when we run a lot of applications.
Yeah.
Are there any tools dedicated to measure this energy consumption?
I know there are some that don't work that well. I heard of Kepler, for example, for Kubernetes. I also heard that it didn't work that well, but it's been done. What I'm basing on is that for this part you talk about, the application part, which is this second part, you have a paper from people from Google that they had a lot of data on their data centers, and they showed that the energy consumption was basically linear in the CPU load. You could do finer models. Now there are people working on finer. Yes, the more CPU, yeah. You have to pay that base energy consumption for turning on, and then it's roughly linear. And you could make finer models because they did that on cloud workloads. For example, we know that memory consumption also interferes. So if you look at some applications with also considering the RAM and maybe some consume a lot of RAM, some not, then it would be different. But the same work hasn't been done on the memory part. So it's harder to assess. In our case, we just look at CPU.